So this brings me to the last part of the lecture today, which is the concept of linearization of nonlinear systems. Of first order ODEs. This is a very useful concept that can allow us to use linear stability theory, the stability theory that we just developed for linear constant coefficient systems, on nonlinear systems. And it breaks down to, a good analogy for what it breaks down to is to think of approximation of a nonlinear function using the tangent line. So recall that in 1D, if you have a nonlinear function of x, say y equals g of x at any point, you can find the linearization or the tangent line approximation of that function. And in a very small interval around the point x naught that you're finding the linearization at, if the function is differentiable, the linearization is the best linear approximation of the function. So consider the following nonlinear system of ODEs. Xi prime is equal to g of xi with some initial condition. Xi of t naught is equal to xi naught. Remember that this is a system of n nonlinear first-order differential equations. Xi1 prime is equal to g1 of xi1 through xn. This is an autonomous system as well. All the way through Xin prime is equal to Gn of Xi1 through Xin. With initial conditions, Xi1 of t naught is Xi1 naught, whatever that value is, all the way down to Xin of t naught is equal to Xin naught, whatever that initial condition is. Now suppose we wish to linearize system star around some point in n-dimensional space Xi star. This is, say, come up with the best linear system of ODEs that approximates around Xi star the exact solution. So Xi star is a point, and we have some initial condition that's close enough to Xi star, Xi naught, but that in general the solution might orbit around like this. And if we get close enough to Xi star, we want to find a linear system that approximates the solution to the actual solution. So if we zoom in close enough to xi star, we expect that the linearization will hopefully be a good approximation of that true solution. And this is directly possible to do. What we do is define the distance h, the distance vector h, which is xi minus xi star. Remember, this is the same thing as saying that xi is equal to xi star plus h. And h in general will depend on t, just like xi depends on t, but xi star is a fixed point. Well, if we differentiate this relationship, we get that h prime is equal to xi prime minus 0, because xi star is fixed, which is g of xi, which in terms of h is g of xi star plus h. And this is where we recall from multivariable calculus the multivariable Taylor series expansion. For each I, from 1 to n, we have that hi prime is equal to gi of xi1 plus h1, xi2 plus h2, and so on and so forth, all the way up to xn plus hn. Which, as long as gi is a nice enough function, which, remember, we're assuming that g and its first derivatives are continuous, this will be equal to gi of, this should be xi1 star here. xi1 star, xi2 star, xin star. This will be equal to gi of xi star plus the first derivative of gi with respect to xi1 evaluated at xi star times h1 plus first derivative of gi with respect to xi2 at xi star times h2. We go all the way up to the first derivative of gi at xin star with respect to xin and xi star times hn plus some error term of h, where the error term decreases to first order in h, or the limit as h goes to 0 of the error term ei of h over the size of h has to be 0. So ei goes to 0 faster than the size of h. In our vector language, this is the same thing as saying that the derivative of the vector h is equal to the vector g of the point xi star plus the vector gradient of g1 at xi star dotted with h. But this happens for every I. So the second component over the gradient of g2 at xi star dot product with h, and so on and so forth for each one of the gi's all the way down to gn dotted with h plus a vector error term depends on h. Right. Epsilon of h is just all of the epsilon 1, epsilon 2, epsilon 3, all of the error terms for each one of the Taylor series expansions. Where you can say that the limit as h goes to 0 of the size of this error vector function over the size of h has to go to 0. This encapsulates all of these conditions. And so this is equivalent to h prime is equal to g of xi star plus the matrix of partial derivatives dg1 dxi1 dg2 dxi2 all the way to dg1 dxi2 all the way to gg1 dxin dg2 dxi2 xi1 d g2 dxi2 all the way over to dg2 dxin. This goes all the way down to dgn dxi1 dgn dxi2 dgn dxin. But this matrix evaluated at xi star times h, then lastly plus the error vector epsilon of h. And so this is an exact equation. This matrix right here is called the Jacobian matrix of the nonlinear system, or the Jacobian matrix of g, the vector function g, at the point xi star. We denote this as j of g evaluated at the point xi star. So a more compact way of writing the system is G H prime equals G of xi star plus the Jacobian matrix of G at xi star multiplied by H plus the error vector epsilon of H. And what's really cool here is that right, if H is small enough, right, what does this mean? Well, this means that the xi of t is close to xi star because xi of t is just xi star plus h of t, and that also means that the size of the error, E of h, is equal to the size of epsilon of xi minus xi star. If this is small enough, this error is approximately 0. And it goes to 0 faster than h does. And so xi prime is approximately equal to, it's exactly equal to h prime. But if this is small enough, then this is going to be approximately the G of xi star plus the Jacobian matrix of G at xi star times h. And this is called the linearization of star. Specifically, this generates an inhomogeneous constant coefficient system called the linearization of star. So for fixed xi star, then the inhomogeneous linear constant coefficient system denoted by star L, which we'll say is eta prime is equal to G of xi star plus J of G of xi star times eta eta naught is whatever h naught is. Is called the linearization. Of star around or about the point xi star. I want to make a note here. If xi star is an equilibrium point, of the nonlinear system star, then g of xi star is 0, the 0 vector, and the linearization star L is a homogeneous. Linear system. Which we know how to classify the critical points of. Because this thing, this vector, will be 0 at any critical point. So what we've just stumbled upon here is really quite incredible. And what it's saying is that at a given point in xi star, if we get close enough to xi star, we choose an initial condition that's close enough. Think of zooming in really close to xi star. The initial difference here is h naught, and the linearization is going to behave exactly the same as the actual solution if delta is small enough. Which means that even for a nonlinear system, if it determines if the Jacobian matrix is non-zero, we can go through and use what we've done so far to classify the critical points of a nonlinear system, which is incredible. So I'll end by going over a couple different examples of this. The first is the damped nonlinear pendulum. Where xi is the angle and angular velocity of the pendulum. The system of differential equations is omega, or xi dot equals omega, and then negative r omega, negative g over L sine of theta. This is our vector function, g of xi. The Jacobian matrix of this g of xi is going to be d g1 d theta, dg2 or dg1 d omega, dg2 d theta, dg2 d omega, which is equal to 0, 1, negative g over L cosine of theta, then negative r, and furthermore recall that the equilibrium points of this pendulum problem are when omega is equal to 0 and theta is equal to 0 plus or minus 1 plus or minus 2 and so on and so forth. Or, theta is equal to n times pi, where n is equal to these values. So on and so forth. So the linearization at an equilibrium point, at any one of these equilibrium points, g of xi star is equal to 0. This is going to, either any of these values for omega or theta is going to make this g right here equal to 0. And the linearization then will be around any one of the critical points. The eta prime is equal to matrix 0, 1, negative g over L cosine of n pi, then negative r times eta. With eta of t naught equal to whatever h naught is, where h naught is a vector that separates from this critical point. So we have a theta axis and an omega axis. Our equilibrium points look like this, and h naught will be a point that separates by a certain distance from one of these critical points. So cosine of n pi is going to be negative 1 to the n. If n is odd, it'll be negative 1, and if n is even, it'll be positive 1. And if this is our matrix A, you can go through and get the eigenvalues of A, or use what we did at the very beginning of the lecture, which is use the invariance. The trace of A is just going to be negative r, and Q, where this is just the eigenvalues summed together, or the sum of the diagonal points of the matrix, and Q is going to be the determinant of the matrix A, which is going to be 0 times negative r minus g over L times negative 1, which is just g over L times negative 1 to the n, where n any integer. And so we have that p is always less than 0, and q is greater than 0 if n is even, we have that p is less than 0 and q is less than 0 if n is odd. Which means that for odd values of n, we expect your solution to be asymptotically stable and for even values of n, we expect there to be a saddle point. In the linearization, but because the linearization is a good approximation when we're around the actual system, when we're around the critical point, when we're very close to the critical point, this is enough to classify what we expect. And sure enough, if we do a plot of this system, this is exactly what we see. This is a plot of numerical solutions to the system in the phase plane. And we see very clearly that at the odd values, at the even values, this corresponds to n equals 1, n equals positive 2, n equals negative 2. We have asymptotically stable equilibrium points. And at the odd values of n, corresponds to n equals negative 1, n equals positive 1, we have saddle points. Which is a very, very neat method. So let's go through and really kind of practice this. We'll do this now for the non-dimensional Lotka-Volterra equations, which we talked about in class before. These are the predator-prey equations from our population models. So for these, the dimensionless prey population is x, the dimensionless predator population is y, and the system of differential equations ends up being the time derivative of xi is equal to a times x minus b times xy minus c times y plus d times xy. This is g of xi. Where a, b, c, and d are all positive parameters that are found when non-dimensionalizing the predator-prey equations and represent the growth of the prey in absence of the predator, the rate of decrease in the prey due to the predator eating the prey, and same thing, this is the shrinking of the predator in absence of the prey, and this is the growth of the predator population due to consuming the prey population. The Jacobian matrix of this system is the matrix A minus by is the partial derivative of this with respect to x. The partial derivative of this with respect to y, which is negative bx. Partial derivative of this with respect to x is dy. The partial derivative of this with respect to y is negative c plus d times x. Call that the equilibrium points of the system of differential equations star for this problem are the points 0, 0 and the points c over d comma a over b, or x equals 0, y equals 0, and x equals c over d, y equals a over b. And it should be clear that when you plug these two equilibrium points into the function g from before, you get that g of these points is equal to 0, 0 for either of these two critical equilibrium points. So the linearization then, we'll do 0, 0 first. At 0, 0, you get eta prime is equal to a 0, 0 negative c times eta, where the trace p is equal to a minus c, and the determinant q is equal to negative a times c, which is less than 0. So we expect that the 0, 0 point is a saddle point. And if we consider the other equilibrium point, which is the point c over d, a over b, you end up getting the linearization eta prime is equal to 0, negative bc over d, positive ad over b, 0, times eta. This is our a, and p is equal to 0 then, and q is equal to this times this minus this times this, which simplifies just to positive AC, which is greater than 0, which classifies the critical point C over D, A over B, as a center, or more specifically, a stable center, where around this point we expect the solution to oscillate, but not converge. And sure enough, this is exactly what we saw. So if we open up a numerical plot of solutions in the phase plane, and this is actually a combination of some numerical plots along with the exact analytical solution, which we obtained. Right, we see exactly that. That the origin is a saddle point, and the other critical point right here is a stable center, but it's not asymptotically stable because the solution is not converging to that point. So this is really incredible. These two examples, I think, are good enough to emphasize the power of linearization for classification of critical points, but also for just getting the solution in a very small region, getting what the solution behaves like and what it looks like in a very small region localized around a point for a nonlinear system. It is very cool. But this is all that I wanted to talk about for this lecture. Thank you very much for tuning in. I hope you had a fantastic day.